Okay, previously we stopped at these slides. Today we learned something, not something new. Before this, all our axes is x and y, and you see collinear motion, you will split into normal and tangent. So for today, we will recall that there is one more coordinate system, which is called polar coordinate or cylindrical coordinate, that is defined by a principal center O, position R, and theta, which is anti-clockwise positive, and the elevation is defined as Z. So we are now in chapter 2. So one famous equation is F equal to ma. So all the force we can convert it into motion ma. So same with here. All the force acting on these particles, blue particles here, okay, you can split into r-axis. So r-axis, if you're in a cylindrical coordinate, your r will always positive going out. Like you draw a circle, your r will always go out to represent that the curve is getting bigger and bigger. So in this case, your r is going out, and then your theta anti-clockwise. So as you can see, anti-clockwise positive, then the angle will be positive going that way, okay, because of anti-clockwise direction, okay, positive going this way. And then the elevation Z go up is positive as usual, right? So when you write your equation of motion, all the force will create motion, F equal to ma. So you generate the equation on the left-hand side, you will see all the forces. On the right-hand side is all the ma. So when you solve this kind of problems, you can group into their respective axis. So for example, you can group R in R. So all the force in R direction in MA, acceleration in R direction. Same with other two, huh? Make sense? Yeah. So always when you solve question in engineering dynamics, always be specific in direction because we're dealing with vector, right? Always group in that particular direction and then you solve it. If you cannot solve, go to another direction and then try to see if there anything that you can use. Right. So let's and this is just a recap. As you can see on the screen, you look at the particles and the blue line, you know that this is a curvature motion. So curvature motion, still you have position defined by R and theta with the anti-clockwise direction, and the P, F, and N, they are the force acting on the object. And yeah, and you can still do the same. You can still do the same. You group all the force, P, F, and N as a force, and it will create motion in R direction, theta direction. In this case, there's no B because it's in the planar form, two-dimensional, B0. All right. Now, let's look at example 7. So you have a smooth ring. So you know that when you see the word smooth, it means you don't have friction. Although don't have friction, you will always have a contact surface. So contact surface, you will always have a normal force. Okay, so chapter 2, when you draw free body diagram, always remember you will have two forces. Okay, in chapter 2, all forces. So all the object will always have a mass. So mass will always pull by gravity, will create your weight, mg. And if there is a contact surface, whether there's a friction or no friction, every time there's a contact surface, the normal force will always acting on the surface and perpendicular to the object. Okay, so these two are always the same. Always remember to put into your F equal to ma on the left-hand side, the force component. So in this case, how you know that you need to use the polar coordinate or cylindrical coordinate? You look at the question, you will see theta dot. You will see theta dot. Then this kind of question actually expecting you to use polar coordinate r theta in your solution. So you have a double collar here. So arm AB, cylindrical guide rod here, and if the arm rotate with a constant angular velocity theta dot with 3 radian per second, so radian per second, you should able to convert 1 radian equal to how many degree? Okay, so 2 pi radian equal to 360. So you do the conversion. Okay, so you look at the diagram here. Where is the direction? Direction is anti-clockwise with the blue arrow. Okay, so determine the force the arm exerted on the collar at the instant 45 degree. You freeze the time where the collar reach 45 degree. So 0 to 45. Okay. Motion is in horizontal plane. Okay. So what is your object here? What is your target in this question? This collar. Right? You have two objects. One is this outside the collar, this one, and another one is at the back. We have two mechanisms there, right? So this is your target. So for chapter 2, you draw free body diagram. And if you look at this diagram, you know that you are dealing with curve, you're dealing with circle. So when you deal with circle, it's highly recommend you consider drawing the normal and tangent axis in your free body diagram. So you draw the object. Again, you have two shapes there. One is the horizontal rectangular, one is the slanted rectangular. Okay, so the question asks you to focus on the force, the arm exerted on the collar means the force of this arm acting on the horizontal collar. So you draw normal and tangent. You should understand why normal is pointing in. In this case, I draw the T to the right, but you can draw T to the left because the angular velocity is anti-clockwise. So actually you're moving from here to here, right? So this collar will moving this way. So the motion will be moving this way. Tangent always follow the motion. So T will be on the left-hand side. Okay, so you can make correction in your notes, right? The T actually is on the left-hand side, positive to the left. But if you put T to the right also, cannot say wrong, but you will get negative sign in your answer if you want to find the T direction. Then you put inside two more axes that you learned 5 minutes ago. When you see theta dot r, it means that you need to include the radial axis and angle axis. R axis, how you know R axis? So in this case, you follow this object, the one that slanted. So this is the R, right? R increase in this area, in this direction. So going up. Then this anti-clockwise angle. So angle is positive, go up. Makes sense. And R and theta always, in this case, 90 degree. Okay. Now, once you know coordinate system, then you put inside the force. What are the force you have when you have contact surface? Normal force, right? And also your weight. So you have a normal force acting for the C is acting on the round ring. Why the arrow is pointing this way? Why? why the end is not pointing up but pointing down? Hmm?
It's on the ground supply.
Okay, so end is pointing down because there's a contact C onto the gold ring here. Okay, and there is a force exerted of the AB, this rod AB, there's a pin here. So pin, this AB is this slanted rectangular. So also have contact surface but with the pin. So the direction is 90° to the slanted rectangular, but through the center point. Okay. Uh, okay. Then you continue with the equation of motion. All right. Of course, you can overlap with the kinetics diagram. Kinetic diagram is moving this way. All right. So equation of motion, you write, we have two direction. One is radial direction and angle direction. Okay, again, when you see the question with theta dot, with the r and theta, expecting you to use polar coordinate or a cylindrical coordinate. So your F will be in r direction and theta direction. Okay, so your r direction, as I mark in on the screen here, your r positive going along AB. And your theta is along the 45, the angle direction, this direction. So what are the force in r direction? So NC you split into r direction, theta direction and r direction. You split into 1 and 2. Okay. So why negative? Because it's opposite the r. The vector is pointing this way. So you get negative there. Right. Why 45? Because it's asks you angle at instant 45. M is 0.5 kilogram. AR, we don't know. So it just remain. Then theta also same. Theta angle, you split this one and using AB. Right. You should understand why AB is not, you cannot group under R direction. Okay. So you will arrive at this equation. Then you rearrange. Okay. You can put in your, you know that kinematics is related to F equal to ma, is more towards acceleration. So you on your kinetic diagram, you include AR. In this case, we already overlap free body diagram and kinetics diagram. Okay, so AR this direction, A theta this direction, and this AR and A theta they are vector. Vector have direction and magnitude. When you want to find the magnitude, square AR plus square A theta square root, you get the resultant magnitude, and to find the angle, you use trigonometry. Right. So there's one equation that you need to recall when you learn about cylindrical coordinate previously, where you need to use the r dot, and r double dot. Okay, so these are the differentiation. So go home and read the appendix C to recall, right? So you get the at angle 45, you substitute inside here. R when theta 45, what is your R? When theta 45, what is R dot? Same with the R double dot. Okay, you get the answer. Okay. So when you substitute the answer, you get R dot, R double dot. Huh? Okay. The theta double dot you extend from here. you are given theta dot 3 radian per second. You differentiate this one more time. This is a constant value, you get 0. So all the value double dot inside this equation, this one 0. Okay, so recall this equation. When you deal with r theta or cylindrical coordinate, you need to use this equation. AR equal to R double dot equal to R theta dot square, and A theta equal to R theta double dot plus 2R dot theta dot. Remember this one when you see cylindrical coordinates. Okay, and this is why we need to do double differentiation for your R, double differentiation for your theta. Because we need this one to calculate your AR and R theta, A theta. Okay, you substitute, you get the answer. Then once you get your AR, you substitute inside the previous equation, you get your NC, right? Then you get your A theta, substitute here, you get your FAB. Okay. Example 8, go home and read. This is another example on how you use the equation. Okay. With this, we conclude chapter 2. Come and read lots of steps. Okay.